Hello, today I'm going to present you a machine learning method to predict the quality of transmission of candidate lightpaths in optical networks. Predicting the quality of transmission of a lightpath prior to its deployment is a step of capital importance for an optimized design of optical networks. As of today, state-of-the-art quality of transmission estimation techniques are either exact analytical models estimating physical layer impairments, such as the split-step Fourier method, which provide accurate results but incur heavy computational requirements, or margined formulas such as the popular Gaussian noise model, which are computationally faster but typically introduce high link margins that lead to underutilization of network resources due to the inexact knowledge of the values of their numerous input parameters that may occur in real deployment scenarios. To better understand such limitations, let's consider a simple example. We have a network with some lightpaths already installed and a new traffic request to be served. We would like to know if a given parameter configuration for the candidate lightpath would lead to an acceptable bit error rate. Unfortunately, some inputs required to perform an analytical calculation of the bit error rate are not exactly known. For example, the amplifier noise figure may deviate from its nominal value due to aging, or the inter-channel interference may exhibit variations due to dynamic traffic. Nevertheless, we could learn precious insights on which lightpath configuration should be used by observing the quality of transmission of already established lightpaths. Therefore, machine learning emerges as a promising approach to quality of transmission prediction, as it could exploit the knowledge extracted from field data during an initial training phase to build a fast and scalable prediction model without need of leveraging analytical frameworks. However, the training phase of such model must be carefully designed to ensure accurate predictions. Following this intuition, we propose a machine learning framework that takes as input a vector of high-level features characterizing the candidate lightpath and predicts the probability that the bit error rate measured at the receiver of such lightpath will stay below a predefined system threshold. Optionally, the input vector may also contain features characterizing the spectrally nearest left and right channels of the lightpath under consideration. The machine learning model is trained with a number of synthetically generated samples where the ground truth probability is calculated by means of a transmission simulation tool. We obtained some numerical results considering as reference scenario the Japanese national optical network and assuming a flexi-grid with 12.5 GHz granularity, transceivers operating at 28 GBauds with 37.5 GHz optical bandwidth, and 6 possible modulation formats ranging from 2 to 64 constellation points. We generated 2 sets of 90,000 samples by randomly selecting pairs of source destination nodes and associated traffic volumes to be served. For each traffic request, we consider the 3 shortest paths and each of the 6 available modulation formats. One dataset was used for training and the other for testing. Results show that 1,000 samples are sufficient to achieve very high performance in terms of area under the receiver operating characteristic curve, as graphically depicted also by means of a scatter plot. In order to show how the proposed framework could be leveraged to take routing and spectrum assignment decisions, let us assume that a 500 gigabits per second traffic request generated by node 7 and destined to node 8 has to be allocated in the network. We could query the machine learning model to obtain the predicted probability of not exceeding the bit error rate for the 18 combinations given by the 3 shortest paths and the 6 available modulation formats, and then use the outcome to choose the best one. As you see, the predicted values closely approach the ground truth ones reported in the bottom part of the table. Thanks for your attention. In case of questions, do not hesitate to contact us via email. My name is Cristina Rottondi and I am Assistant Professor at the Department of Electronics and Telecommunications of Politecnico di Torino in Italy. This study has been co-authored by Alessandro Giusti from the Dalle Molle Institute for Artificial Intelligence in Lugano, Switzerland, and by Professors Luca Barletta and Massimo Tornatore from the Department of Electronics Information and Bioengineering of Politecnico di Milano.